Um, so good afternoon, everyone. So, so my topic is related to the social networks and how we can use the social networks with the homophilic preference for the user's representations. So let me first start with the very well-known problem in the recommender system is called stats. So where the users don't have enough data, so to get understanding the user preference. So one way is they rely on the site informations, like they using the text description from the item size. Or another one is they rely on the social networks. Like even you don't know much about that user, but if you know about the friends and the reference of the friends, so you may guess the preference of that users. So I will quickly go through the concepts of homophilic preference. So let's pick examples. If we have the user A and B, they have their own preference. So how to recommend for the user C if the C is the constant users. So we rely on the connection in the social network. If the B have a closer relationship with the, if C have closer relationship with B, so we recommend the similar items. So the idea behind is if the users have the closer relationship in the social network, so we suppose that they will have the closer preference. So our research question is how to rely the social network for the user's representation to improve the item adoption's prediction task. So one possibility is we can rely on the matrix factorizations. Given the ratings or the item adoption, you can factorize into the users and the item size, and you can apply the social networks constraints in the user-specific parameters. But we still have another approach. So we rely on another framework, the Restricted Boltzmann Machine for the user's representations. So I will describe one of the first was using the RBM for the user's representations and in the context recommender systems. So the overall structures of the model is the IBMs. Actually, they just a bipartite graph with the bottom layers here. The visible units it represent for the list of the movies. Let's say for the first movie, they have the rating of 3, and this will be followed by the 3 missing movies. And that's the missing movie will be ignored when making learning the models. So on the observations at the visible unit will be encoded into the hidden layers. And what the IBM learned is they learn the concordance of the item ratings. And we consider the hidden here is for the user representation because it captures on the observation on the ratings of the data users. So it's represent for the data users. So our contribution here. So most of the reviewers was they successfully applies the social network in the context of the matrix factorizations. So we curious and we interested with another observe based on the IBMs. One difference with the matrix factorization is you know that's in the MF-based, so we have the user-specific parameters. But in the RBM, so we on the user we just share the way W, and we don't have the specific parameters for the users. So that's a little the difficulties how to integrate the social networks because you know that the social network this affects on the user size. So without the parameters, so this little difficulties. And we explore just instead of using the pricing direction, so we apply into the problem like item adoption. So we consider on the users on the 0 rating items. So here is 2 proposed methods. For the first model, so we consider the social connections in the network like another observation beside the adoption. And the second model, so we rely on the network structures to make the sharings in the representations. So I will go into the detail of the two models. Let's pick examples for the first models. Let's say we have the B and C, they have the share connection with the user A in the social network. And B, she have her own items. So to recommend for the like the consult user C, so we hypothesize that the user, if they have the similar strengths, so they will adopt the similar items or the preference, so will be closer. Somehow the preference of user B will be transferred to C throughout some shared friends like A. And how to model that? So at first, in the items adoptions side, so we produce the binary vector X. And from the social connections, so we have another binary vectors Y. And for each unit here to activate that is represent like from the item size, so the activate node here determine whether or not the users adopt that items. And it's similar to in the social network size. If the user have the connection with that another user, so we activate that unit. And so we want the model try to learn the co-occurrence of the social connections and the item adoptions. So if we can find the patterns from that two sides of observations. So if the user have even they have the few numbers of the rating, but if they have the connection with another users appears in the pattern, so we can easily to predict the item from the item adoption size. So one way to deal with that, so we just make the bindings from the two sides of observation X and Y by the shared hidden layers. And the idea is we try to learn the crossing patterns between the two sides of observations. And each side observation is like the two sides of the wing, so we just simply call the models like the wing. So that's the idea for the first models. So in our second models, so we rely on the network structures. The big examples for the previous work, they just only have one RBM they share for across the users, and we will captures the global patterns. But we want the models besides the global patterns should be captured the local ones. This means that we want the user have a closer relationship. We want the neighbors they share their own preference. And one way to deal with that, so we're going to go with the DBM models. So the DBM one is actually it's just it's similar to the IBM. At the bottom is still the visible unit, and it will be encoded into the multiple hidden layers. And this allows the signal from the bottoms propagate across the hidden layers. Let me give an example to clarify the ideas of the second models. Let's say I just have the simple network just 5 users, and they considers the first users if the first user he have the connection with the user 3 and 4, and we rely on the DBM structures. So at the bottoms, here is still the visibles for the user 1, and all the users still share at the middle layers. But at the top layer, so we integrate the network structures. Because user 1 just have a connection with the 3 and 4, so we activate the first, the third, and the fourth users. For the users don't have the connection with the first users, so we just drop that users when encoding from the bottom layers. So the idea behind this model is actually we try to create extra space to make the user that if they have the connection in the network, they have a small space to make the sharing. And we call that the model is like the social RBM diff. So that's our two proposed models. So I will quickly go into with the models learning. We use for the activation functions inside of the visibles. You can use the two kinds of the functions. For the first one, like the Gaussian version. So because we consider on the 0 and 1 rating, so if you use the Gaussian, so it's fit better because you can consider the confidence of the Gaussian. Or you just simply using the logistic function. About the hidden layers, to activate it, you're just using the logistic. So on kind of models here, undirected models. So the energy function will capture all the connection in the models. And so for the wing one, so you just simply see that for the first two is capture the connections from the hidden to the two sides of the observations. And we include wisdom bias. We should maximize the likelihood, and we follow the quantitative division algorithm. So actually, in this algorithm, just for each step, so let's try to minimize the data and the model expectation. For in the model's expectations, PN here, you can use the Gibbs tumbling to approximate that. About the model inference. So given the observation, so we at first we infer the hidden layers, and then we go into with generate the ratings. And in the social IBM diff, so we use the fully factorized to approximate the posteriors, and we maximize the lower bounds with the variation of parameters, and we find the peak points. And then we generate the RI with the property to activate the item I's, and we rank that RI to find the top. About the dataset, so we test our two models on the two datasets, the deletion and loss of M. So choose kind of data is very sparse. So you see that the density is very low. And experiment, so we test on the three experiments. So the first one is the model comparison. So we the task here we make the prediction for the items. And because the uncertainty of the zero rating, so we're just using the recall. And here are the results on the last M delicious. So on the delicious, so you can see that two model is significantly higher as our space size. And the last M is because the scale is quite small, so we just show the numbers here. So we say that the social networks have the information, so we try to create the performance when you compare with the random network. And to generate a random network, we try to reserve the degrees of the nodes in the network, so we just simply swap the edge in a network. And so here are the results. The blue one is for the social one, and the red for the random network. And for in the two sides, in the two data sets, so you see that the effect of the social network is significantly higher. So in terms of the effect of the social network is actually different from the two data sets. If the data set is about the online bookmarking, so when you swap the edge in the random network, so it affects a lot. But in the last M, actually it's about the item here, the artists. So some well-known artists will be dominated. So by exchanging the edge in the network, so it doesn't have much effect. So it leads to the gap in the last FM lower than in the deletions. And in the third experiment, so we indicate that given the latent user representations, so we try to reconstruct the social network, because we claim that the latent representation will in our model will bring the users have the connection in the network closest, and we're using the map metric. And so here we result in both our proposed models is actually have the links predictions, the link reconstruction higher than the RBMs. So this means that it brings the users have the connections in the network closer by the diff and the Nguyen structures. About the conclusions, so we address the problem of how to integrate the social network into another frameworks like the RBM. It's significantly different with the ML-based approach, and we propose the two kinds of models. So first is we learn the crossing pattern, and the second is we using the diff to make the share in the subspace. In future work, so we try to apply the Gaussians to fit the patterns in the zero ratings, and we will explore to compare with some standards based on the matrix factorizations. So thank you, and any questions?
Thank you. Do we have any questions from the audience? So in terms of baseline comparisons, did you look at any work in the area of like link prediction, where there are some much more simple metrics that can be applied for link prediction? Because essentially you have a graph between users and items, and so you can turn it into the task of trying to predict a link between two disconnected entities.
So can you repeat what is the point?
I'm asking, have you looked at any baseline comparisons with
Yes.
some of the existing work in link prediction?
So you're asking about the baseline?
Yeah.
And so,
do you have any results from a baseline, or have you looked at them?
So the baseline here, in the baseline paper, so they compare the RBM with the matrix factorization, but it's actually they test on the very big data like the Netflix, and actually the RBM's approach, so they said that actually it's suitable with the big data.
Sorry, could you repeat the last point?
The IBM approach is actually suitable with for the big data set. So in the baseline papers.
Mm-hmm.
Yeah.
Okay, thank you very much. Thanks our speaker, and thank you to everyone for attending this session, and I guess we'll be seeing you at the banquet later. Thank you.